Hello chemistry students. So we're going over now the second method on how to balance redox reactions. The first one in a previous video was the half reaction method. So let's get started. Now you'll see that there are some similarities and some differences. This one seems to be shorter than the previous. Let's start. So like the previous example, you begin by balancing rather by assigning oxidation numbers. So I'm going to rewrite this equation here. So before I start, I should go over what it's asking. So it's asking us to balance the redox reaction given, and it says that it occurs in a basic medium. So we'll have to make sure to consider that last step similar to the half reaction method of adding hydroxide ions for every hydrogen ion present. But I don't think I'll have enough room to neatly or somewhat neatly assign oxidation numbers at the top. So I'm just going to rewrite. And yes, these are all aqueous, like in your note. This should be, I should write aqueous signs, but I know I'll forget. So don't mind that I don't. Okay, so I like this example because hydrogen appears on the right-hand side of boron, which you might think, well, if our options for hydrogen from our previous lessons are that it has a +1 or a -1, well, if it appears on the right-hand side, you might think it has a minus or a negative charge, a -1 charge. In this case, it doesn't, so you're always looking at which element has the greatest electronegativity when you're comparing hydrogen to whatever it's attached to. And if boron in this case has a greater electronegativity, it's further right in the periodic table than hydrogen is. That just means that it's more able to attract electrons to it, which means hydrogen is then going to lose electrons and it's going to have a positive charge instead. So hydrogen is going to have a +1 charge as our oxidation number, which means boron has to have a -5 if you're going to accomplish that overall -1 charge seen in your question. Okay, so boron and hydrogen, here are their oxidation numbers. Okay, now continue. Let's look for, well, this is easy. Might as well show this one here. This is a -1 charge because it says it's -1, so that was pretty simple. Then oxygens. Oxygens are good. Again, this is a 3. Oxygens are good to start with because we know that that's going to be -2. Okay, so if this is -2 and there are 3 of them, it contributes then a -6 charge to an overall ion that should have a -1 charge, which means chloride has to have a +5 charge. Okay, moving on. This is borate, and I don't know why I wrote a 4 here. This should be a 3. This is borate. Borate helps to think about these ions separately at the beginning. Borate has a -3 charge by itself. So the overall charge on the whole ion or molecule here, it says it's a -1. So if we can just work on borate though. Borate, we know oxygen is going to have a -2, right, which will contribute a total of -6, right? So -6 in total from oxygen, and that has to add together with boron's charge, with just one boron, to give us a -3 charge. So boron in this case has to be a +3, right? So boron has to be a +3 to give borate that -3 charge, and oxygen is always -2. Okay, so we know that borate has a in total has a -3 charge. Because there are 2 hydrogens and an overall charge of -1, hydrogen has to be a +1. Because there are 2 of them, it would contribute a total of +2 charge plus a -3 charge gives us a -1 charge, and look, that's what we need. So you can double check that if you want in that way. Okay, so here we have our oxidation numbers all assigned, so we're done our first step. Okay, now it says determine the number of electrons lost or gained per atom. So it's essentially, although you're not breaking this up into half reactions like the previous method is, or asks you to do, you are still kind of considering them as separate half reactions. Okay, so I'm going to have to rewrite this redox reaction and their oxidation numbers. Okay, I'm going to choose a different color here to show you oxidation numbers. Okay, so Again, just going to rewrite these oxidation numbers: -5, +1, this was +5, this we know is -2, +1, +3, -2, and this is -1. Okay, now let's look at, even though this is in half reaction, let's still look at the half reactions here. So here we are. Those are related. How we know they are? Because they have boron, right? We know that oxygens come and go, right? It exists in a solution of either an acid or a base, so oxygens are present because of that aqueous solution. So find whatever matches. Boron is here, that is one part of the reaction, the other half is among these two entities there. Okay, so we're going to look at each one, and we're going to see how these oxidation numbers change. Boron goes from -5 to +3. So we have to think, has it become more negative? In other words, have we added electrons to it, or has it become more positive, and have we taken electrons away from it? So in this half reaction, we can say that we have lost electrons. So if you want to think of this as a number line, or just add these absolute values, whatever works for you. -5, to get rid of these -5 electrons, you have to take them away, and then to further make it more positive, you have to take another 3 away. So we're going to lose, lost, therefore 8 electrons, and then we know that's going to be the oxidation half reaction. Now chlorine goes from +5 to -1. Okay, so it's become more negative, so that means it's added, we're adding electrons to this, and it therefore would have gained, to go from +5 to -1, it would have gained 6 electrons. This is your reduction half reaction, right? So there we go. We've determined the number of electrons lost or gained per atom, and we've somewhat broken this up into half reactions like the previous method, or similar to the previous method. Step 3, multiply each half reaction by an integer such that the number of electrons cancel. Alright, so this is where we're balancing charge. So balancing charge comes first in this method. So I'm not going to write out the full reactions again, but we can say that our oxidation reaction involving BH, right, BH4 and so on, that has lost 8 electrons, and our reduction reaction, right, involving chlorate, okay, that has gained, right, it's gained 6 electrons. Now we're going to try to find, similar to how we did in the last example, we're going to try to find a lowest common multiple. So lowest common multiple between the two, because we know that the electrons that get lost have to be gained somewhere. These numbers essentially have to match. So the LCM for this is going to be 24. So we're going to go back to that reaction now, multiply this half reaction by a certain number so we get to 24, right? It's going to be 3, right? Then we're going to go to the reduction reaction. We're going to multiply that by a certain number from 6 times something to get to 24, okay, 4. So let's do that. And once you do that, and just go back. So essentially, BH4, this oxidation portion is multiplied. We will end up multiplying that by 3, and we're going to end up multiplying this portion by 4, right? So that what we get is this. Okay, so if we look at this now, boron's oxidation number, we know, remember that was -5. If you multiply that by 3, and then multiply this by 3 as well, if you add up all of the charges, you'd see that they all equal 24. So here we have gained 24 electrons. And here we have lost, oops, don't mind that, we've lost 24 electrons. As it should, right? As we wanted that to match, and they have, so we're good with that. Okay, now questions can get a bit more challenging when you're now looking at having to balance this first. Look, it works out really well in this case because we have 3 borons and 3 borons. We have 4 chlorines. You want to double check as you go along these types of questions that those are balanced, and that can happen before or after you start playing around. or you start the question itself, probably best to happen before, but in this example it ends up working out. Okay, next step. So now we can balance atoms, right? Again, you're going to use H2O to balance oxygen and hydrogen ions to balance any of the hydrogens. Okay, so looking back, let's look back. Maybe we'll switch pen colors again. Where is it? Here we go. Okay, so let's look at our oxygens. So here we have 4 times 3, 12 oxygens. Here we have 3 times 3, 9. So we're going to balance oxygens first. It looks like we have 9 on this end and we have 12 on this end. So we're probably going to need to add 3 H2Os to the product side, and your reaction is going to look like this. So let's do that. Okay, so here are my 3 H2Os, right? We realized we had to add 3 H2Os to the right-hand side. I forgot a charge. Okay, there we go. So we've balanced oxygens, that part. So now let's look at hydrogens. Here we have 12 hydrogens on this end. Here we have 6 here, 6 and 6. So 6 plus 6 is 12. So it turns out we don't have to add any hydrogen ions. Good, so that part is also complete. Okay, now since this said, moving on to the next step, since this said the question asked us to balance this redox reaction in a basic solution, then we have to add hydroxide ions for every hydrogen present, for every hydrogen ion present. But in this example, there are no hydrogen ions present, right? So this step, despite it being in a basic solution, is actually not necessary, right? So only do that if necessary. So we can therefore say the answer, therefore, is exactly, maybe I shouldn't rewrite this, but just so that drive the point home that we don't actually need to add hydroxide despite it actually being in a base. I should have given myself more room, but there you go. This is now your final answer. Okay. Post any questions, I can go over and help you answer them. This is just one solution to this particular question. Let me know how else I can help. In the meantime, I hope this helps.